Hello, everyone. Thank you for joining us today. My name is Tegan Clary, and I'm the Vice President of Marketing at Unchained Labs. I will be moderating the seminar today, and I'm very glad you've decided to spend part of your day with us. Before we get the seminar started, I want to remind any of our customers joining us today that Unchained Labs is dedicated to supporting our customers through this challenging time. Please do not hesitate to get in touch with your local salesperson, an application scientist, one of our service engineers, or you can contact us directly at our website if there's anything that you need. We're ready to do everything we can to help you. We will have a Q&A session at the end of the presentation. To ask questions, all you have to do is click on the Q&A, little Q&A button in the Zoom navigation bar, which should be at the top or bottom of your screen. And there you just type your question. We will get to as many of them as we can. And now I'd like to introduce Lisa Kraft, one of our outstanding application scientists. Today, Lisa will take us through how the Hound platform can identify contaminants or particles that can show up in drug development and manufacturing processes. And now I'll hand it over to Lisa.
Hello, everybody, and welcome to today's webinar, Root Cause Particle Investigations with Hound. My name is Lisa, and I'm Field Application Scientist at Unchained Labs supporting our QC products. One of the biggest things to avoid for a drug manufacturer is an FDA recall, which can happen for various reasons, but one of the most common ones is finding particles in the drug product. Here you can see a few examples where mainly glass particles were found in the product and caused the recall. So when you find particles in your samples, what you usually want to do is find out where they come from and eliminate the source of the particles. One step in identifying the source of a particle is usually finding out the material of the particle. A particle could, for example, be an intrinsic particle. For example, a protein aggregate that has formed in your biologic drug product over time. Or it could be a cellulose fiber, a stainless steel fragment, or a polymer. Particles can come from a variety of sources, but knowing the composition of the particle will help you track down where it came from. A few examples. If you find an aluminum particle, it could indicate that it comes from the crimp caps used for capping your vials. Finding a cellulose fiber could mean it was released from towels used to clean manufacturing equipment. A stainless steel particle could come from a bioreactor used to produce the drug product. Rubber particles could have been released by the stoppers used in primary packaging. In general, the more information you collect about your particles, the easier it will be to find the source and eliminate it. Hound is designed to help when particles are found. It provides a unique combination of microscopy to find, count, and size particles, Raman spectroscopy for chemical ID, and laser-induced breakdown spectroscopy, or LIBS, for elemental ID of particles. All those tools can be used in a fully automated way to characterize and identify both visible and subvisible particles. By combining microscopy with 3 different spectroscopy modules, Hound covers a very broad range of materials it can identify. It is equipped with 2 different Raman lasers. With the red 785 nanometer laser, you can identify most organic and inorganic compounds. As fluorescence excitation is usually not efficient when using this wavelength for excitation, it allows for identification of materials that would show a huge fluorescent background when exciting at lower wavelengths. The green laser is usually the better choice for identification of proteins, as it produces more signal and even allows to discriminate between different types of protein. As a third spectroscopic technique, we included LIBS. LIBS measures the elemental composition of a substance and gives great results on inorganic and metal particles. Metals don't show any Raman signal at all, so metallic particles could not be identified with a Raman-only instrument. Here is a bit more detail about the identification of particles using Raman spectroscopy. For each sample, you choose if you want to use the 785 nanometer or the 532 nanometer laser for identification. Or you don't know which one works better and you try both. Raman identification works for particles of all sizes down to 2 micrometers. After a Raman spectrum is taken, it is automatically compared to a database of known materials, and the system will find out if there is a match in the database and tell you the name of that match, as well as a match rank. The match can either come from our standard database that comes with the system and contains more than 150 of the most common contaminants we find in pharmaceutical products, including protein, polymers, cellulose, etc. Or you can create a custom database that contains specific materials used in your production process, like your specific proteins or lab wipes that are used in your facility or other things. When doing this, you have the best chance to find the specific particle source in your lab or manufacturing process. As already mentioned, LIBS allows you to also identify metals that don't emit any Raman signal. When doing a LIBS analysis, we shoot one laser pulse with a very high energy density on the material surface, and by ablating some of the material, we create a plasma. When the atoms in that plasma fall back to their ground state, they emit light, and the spectrum of that light is element specific. So with LIBS, we get information about the elemental composition of a sample or particle. Particles down to 20 micrometer can be identified using LIBS. As for Raman, the system compares the acquired spectra to a database and shows matches and match ranks. For LIBS, we have a standard database containing more than 50 contaminants, and in the same way as for Raman, you can add your specific references to a custom library. This slide shows an example where the spectrum of aluminum crimp caps was added to a custom database, which allowed to identify those crimp caps as the source of contamination particles. As Hound combines Raman and LIBS with microscopy, in addition to particle materials, you get size and morphology information. On the slide, you can see an example how Hound counted the particles on a specific area in bright field and the size distribution it evaluated. When counting, the user can set up size limits so that only particles in the size range of interest are counted and particles are grouped into user-defined size intervals. For particle counting, the lower limit for particle size is 2 micrometer, but in the example on the slide, only particles of 10 micrometer or larger were of interest. For every particle the system detects, it stores size, shape parameters, and the particle's coordinates on the filter. With those coordinates, it can go back to that particle and do an automated spectral analysis to identify the particle material. You define how many and which particles to analyze based on the size and morphological parameters Hound measured during particle counting. In our example here, you could define that only the one particle greater than 100 micrometer could be analyzed, or all the particles in the 25 to 50 micrometer bin, or even define a certain elongation or fibrosity threshold so that only particles that have certain aspect ratios or fibrosities are analyzed. Let's have a look now at how a measurement on Hound is actually being performed. The first step is to prepare the sample, and we'll have a look at two common ways people do this. The most common method for sample preparation is filtration, but for some applications, people prefer to look at their samples in situ, so they want to keep their particles in suspension. For filtration, we mostly use our filter rounds, which are shown on this slide. Our filter rounds are gold-coated polymer foils available with different pore sizes, which are clamped into an aluminum ring. The gold-coated reflecting surface has several advantages that improve the analysis of particles. First, you can do counting in dark field, which gives you an ideal contrast to count all the particles that are on the filtration area. Second, as it is Raman inactive, you don't get any background signal from the gold surface. After filtration, all particles are located on a defined area in the center of our filter. The size of this area is defined by the funnel used for filtration. So when we insert the filter into the Hound, we will know exactly which area to analyze to count all the particles that were in the filtered volume. The wet round is mostly used when people suspect particles in their samples that might get lost or changed by filtration. For example, if you want to be able to identify silicone droplets in your product, you would use the wet round, as those droplets would probably pass through the filter pores during filtration. Like the filter rounds, the wet round has a gold-coated surface to allow dark field imaging and avoid any Raman background from the substrate. For preparing a sample in the wet round, you simply pipette the liquid onto the wet round, apply the cover slip, and analyze on Hound. Once you have your samples on Hound, there are several ways to analyze the samples. If you have isolated a specific particle you want to identify, you would probably choose a method where you just manually find the particle and use Raman and/or LIBS to identify the material. But Hound can also be used to count, select, and identify a particle, or hundreds or thousands of particles fully automated. First, it will capture images of the sample area to create a mosaic image of the area where you expect your particles. Usually this area is defined by the diameter of the funnel you used for filtration. All the particles on this area will be found by binarizing those images, and particle sizes, shape parameters, and coordinates are stored. Based on user-defined selection parameters, using size, elongation, or other shape parameters, particles are then chosen for analysis and automatically analyzed using Raman or LIBS. Here's a screenshot of our software showing the flexibility of setting up the automated identification. On the top left, you can see how you just select the spectroscopy methods you want to use for your sample. For example, you can define if you want to use both Raman wavelengths on each of your particle, or maybe you just want to use the red laser and only try with the green one if you don't get a result using 785 nanometers. For each laser, you can easily set up parameters like the integration time and intensity, and then let Hound do the work. After collecting a spectrum, Hound will compare it to the reference database or databases the user selected to apply for the measurement. This can be the standard database that comes with the instrument or a customized one you create by adding your specific reference materials like APIs, proteins, materials from primary packaging, etc. Hound will find a match rank for each spectrum in your database using the Pearson correlation and tell you the materials it identified together with the match rank. If you have run a measurement with a specific database and want to match your spectra with a different database at a later time point, you can do that also using our analysis software without having to rerun the measurement. So to sum up, this is what Hound can do for you. It will provide chemical and elemental ID of your particles using Raman and laser-induced breakdown spectroscopy. It will give you the number as well as size and shape information about the particles in your sample. You can use it in different modes of operations, for example, quickly identify a few particles manually or automatically analyze hundreds of particles on your sample. And it includes 21 CFR Part 11 compliance tools so that you can use it in a regulated environment. Now let's have a look at two examples how Hound was used for specific applications. The first example is one our contract testing team worked on. A customer found fibers in a product and it caused several batch failures at filling. So they needed to find out where those fibers come from and eliminate the source of the particles. On the slide, we see a picture of that fiber and a Raman spectrum which clearly shows that it's a cellulose fiber. Luckily, the Raman spectrum shows an additional peak at 1600 wave numbers that is not present in most cellulose spectra. So we can use this peak to find the specific source of the contaminant. An investigation was started to find out where in the process those fibers appear. First, lab equipment and supplies were rinsed and the liquid filtered to see where the fibers appear. On the slide, we see examples of 3 of the samples that were taken. First, the rubber stoppers used in vial capping. Then they rinsed the clean-in-place equipment and the tubing that was used in the process. The filters produced from those rinses were analyzed on Hound, and some fibers were found, as you can see on the pictures. But Raman showed that none of those fibers had the additional peak at 1600 wave numbers that appeared on the contaminant fiber, causing the batch failure. The next step was to take samples from any material in the lab that was cellulose and measure the Raman spectrum. Those materials included autoclave bags, paper, towels, even socks and t-shirts. The picture on the slide shows the Raman spectra of all those materials, but when comparing them to the contaminant spectrum, they all didn't match either. So another approach was taken by moving upstream to manufacturing. Again, samples were taken from any cellulose material and Raman spectra were acquired. And in this case, a match was found. Unfortunately, it's the yellow graph, but this one has the peak at 1600 wave numbers, and also the overall spectrum matches very well with the contaminant spectrum. The match belonged to the AC paper from this lab. So now there was a lead for the material, but still it was not clear how it got into the sample. For figuring this out, 3 manufacturing tanks were rinsed and the resulting solution was filtered. When analyzing the filters on Hound, the same contaminant fibers were found again, also showing the characteristic peak at 1600 wave numbers in the Raman spectrum. It finally turned out that the paper towels were used to clean the tanks, and during cleaning the particles were released that caused the contamination. Having identified this contamination source, it could be easily eliminated. The second example is about the analysis of a protein formulation from a pre-filled syringe. The syringe was expelled and the liquid analyzed in the wet round. In this case, the wet round was chosen as we suspected that silicone from the syringe coating might have moved into the liquid, and we wanted to verify that. The pictures show the 2 typical particle types that were found in the sample. On top, you can see droplet-like particles, approximately 8 micrometers in size, that could be identified as silicone using Raman spectroscopy. On the bottom, there is a more amorphous particle, approximately 34 micrometers in size. We took a Raman spectrum of this, and we found that this one is a protein aggregate. Particle counting in the wet round provided us with a size distribution of particles that are present in the sample. The table on the left summarizes the size distribution and shows the number of particles in the user-defined size bins. From this total number of particles, a few hundred were randomly selected and analyzed using Raman spectroscopy. On the right-hand side, you can see the distribution of materials found in the sample, showing that most particles that were analyzed were silicone droplets, but also we found a considerable amount of protein aggregates. Like in this example, Hound is often used to analyze protein aggregation or potential interaction of the sample with primary packaging. I'd like to end this presentation with a slide showing the different application areas where Hound is being used. As we've covered, it is often used to identify contaminants in pharmaceuticals and quality control, production, or packaging. But it has been successfully used in other applications as well, including polymorph screening, measuring size distributions of different APIs in a topical formulation, or finding microplastic particles in beverages. Due to the combination of 3 spectroscopy modules, it covers a uniquely broad range of materials it can identify and applications it can be used for. Having Raman, LIBS, and microscopy on one system means that samples don't have to be transferred and measured on many different instruments, which enables you to get a result easier and faster. So with Hound, you can finally stop stressing out about particles. Finally, I want to thank you for joining the webinar and your interest in Hound. I'm looking forward to your questions and thoughts. Thanks, everyone.
Thank you, Lisa, for that great overview of how Hound can identify contaminants that may show up unexpectedly. We have some great questions that have been submitted already. For those of you that have joined us, you can still ask a question by entering it in the Q&A section down in the bottom of the Zoom navigation bar. So Lisa, let's go ahead and answer some of these questions. The first one here is, how long does it take to analyze a sample using the Hound?
When you analyze a sample with Hound, it depends a little bit on what you actually want to do. And I want to give two examples of typical cases. One typical case where people want to analyze a particle with Hound is when they find a particle or see a particle in visual inspection and need to identify the material of that particle. And the first step to do that would be to isolate that particle from the liquid, which could take maybe just a few minutes if you just fish it out or if you filter it. And then to analyze the particle on Hound, you would usually just do a manual measurement where you use the joystick or our tools to center the particles, and then use the spectroscopy methods to find the material. And you can have a result in just a few minutes or maybe half an hour. Another typical case is you might want to not just analyze one single particle, but maybe hundreds or even thousands of particles. For example, if you find that one of your solutions is unstable, some particles have formed, and you might suspect it's protein aggregates or maybe something else, then you typically also filter the sample first. Again, this may take between a few minutes and half an hour, and then analyze maybe a few hundred particles, as I've said, to get a statistically relevant subset of the particles you see in your samples. And in that case, you wouldn't do that manually because that would take a while. And instead, you would set up an automated run and then let the system do the analysis of those 200 particles. So setting up that run would also take you just a few minutes, where our software would guide you through the different steps, how to set up illumination, particle recognition, spectroscopy parameters, etc. Then you would just hit start and the system would do the analysis. And depending on the number of particles and spectroscopy modules you want to use, this can take maybe a few hours if you do, for example, 200 particles. Or if you want to analyze maybe 2,000 particles, you can start it in the evening and do an overnight run.
Okay, great. Thank you, Lisa. Here's another good question for you. How does someone create their own custom database? And typically, how long does it take for them to add material to that database?
Okay, if you want to add your specific lab materials to a database, you just need to pull a sample, for example, from your API powder, or you cut a piece of lab wipe you want to add to the database, or a piece of plastics that's used in your process. You get a little bit, a piece of aluminum from your vial cap. Then you place it on the instrument and just take spectra. And usually you wouldn't just take one spectra, but a few of them, maybe 5 or 10, and average those just to be sure that you didn't maybe measure on a position that's not representative for the whole material. The software comes with a tool, our analysis tool, that includes options to manage your databases. So you can easily open databases in that tool. And with just a few clicks, you can create a new database or add spectra to a database average spectra. So in total, adding a new substance to a database takes about like maybe half an hour to prepare the sample and measure, and then just a few minutes to add the spectra to the database.
Okay, great. Lisa, you talked about the sample preparation, and I have a question here for you about that. How do we ensure that other foreign particles or other things don't get into our samples when preparing and running samples using the Hound?
Yeah, so typically what people do during sample preparation is they perform the whole process under a HEPA filtered hood so that you are working in a clean environment. When filtering samples, they have some guidelines how to do that, how to make sure that the equipment is clean. For example, running a blank sample through the filtration funnel before running or before filtering the actual sample, to make sure that you don't see any particles that just come from the funnel. And then you transfer the sample from the filtration station to the Hound. This can either be that the Hound is in the same hood as where you do the sample preparation, so that you make sure you don't add any particles during transport. But we also actually see that when we transport the sample in a closed container, like a little Petri dish, that we don't see any problems with particles coming to or being added to the sample.
Okay, great. Thanks, Lisa. Lisa, if I have a Raman library from just another spectroscopy instrument that I want to compare my samples on the Hound to, is that possible? Can I use databases or Raman spectra for matching from another instrument or from a tool I already have?
Yes, so we have a lot of customers who I think Bio-Rad is the most common database that is used, and Hound actually makes it pretty simple to export spectra with just a few clicks. Again, our analysis software has that tool where you manage your databases and spectra. You can export the spectra from a run very simply and then import them to other tools like the Bio-Rad database. Several people do that already.
Okay, great. Lisa, I think this will be the last question for you for the day. The question is, we're working on building an image library of particles as well as spectroscopic characterization. Does Hound do anything to help us build that library too?
Yes, that's actually also a very typical application. I think that's very common when particles are found in visual inspection. People want to keep track of what types of particles they see. So what they do is they have like as you mentioned, a particle library, and Hound can help a lot to create that particle library. And it has several tools you can use for doing that. So first is the imaging part of the particles. When you've isolated them, Hound has a lot of nice tools for imaging particles. We have several contrast mechanisms. We can image particles in bright field or dark field. Or we also have cross polarizers that can make nice contrasted fibers, helping to identify if it's a cellulose fiber, for example. We have different objectives on Hound with different magnifications, so you can get high resolution images of a fiber or particle, or overview images with a lower magnification. If you have very large particles like long fibers, for example, we have tools to create what we call mosaics, where you have not just a single field of view, but you scan, for example, 3x3 pictures with a certain magnification, and the Hound will automatically stitch those together so that you can also from very large particles get nice overview images in a very high quality. And that's also very easy to do because you can just, from a picture of the filter, draw a rectangle where you want to image, then the system will take that mosaic and you will have a nice image of your particle. And then of course you have the spectroscopy tools. You can have your image, but also in addition to the image, you can have a Raman spectrum for that particle, have a LIBS spectrum, and then with those information, categorize your particles and then yeah, create that particle library in that way.
Okay, great. Thank you, Lisa. Thank you for answering all these great questions. Those are great answers. And thank you for a great presentation today as well, too. I want to thank all of you who have joined us today live. I think with many of us working from home these days, I know many of us at Unchained Labs are working from home. For those of us that are kind of non-essential employees, we're not in the office. Our team that manufactures our products and many of our support people are still actually in the office and still working out in the field helping customers when they can. I do think this is a great time to explore new ideas and solutions to problems. So if you would like to have a deeper conversation with our team about the Hound and how it might fit into your work or into your lab, please do get in touch with us. Our team would love to connect with you over a Zoom meeting. This is Zoom webinar, but we also, all of our team members have regular Zoom meeting capabilities and would love to get on a meeting with you and just talk to you about your work and what issues and problems you might be seeing and see if one of our solutions can help you with those things. Thank you again for attending our virtual seminar, and I hope you have a great rest of your day.